Hi, it's Terry Denery of the MathWorks. So let's get into PIDs. So PID controllers, proportional integral derivative controllers. And I have a model here, and essentially this kind of piece of it right here is essentially the algorithm of the PID controller, right? Now, before we start discussing that, why don't we just kind of look at how we did with this. So I create a very simple system, and this is the response we're getting through the PID controller. Essentially commanded it to go to a value of 1, and it certainly gets there. But it takes 1,000 seconds, and in that journey to get there, it goes through quite a bit of oscillation. So it's not a really good response, and because of that, we're going to do what you generally do when you do PID controllers, and we're going to choose better values for these key parameters that define the algorithm. These essentially your gains, your proportional, your integral, and your derivative gain. All right. So kind of zooming in, I want to be clear on why they got the names they do. So derivative gain, you'll see is on the thread that employs a derivative block. Integral gain, of course, on the thread that includes the integrator block. And then proportional just takes this error, the difference between what we're commanding and what's being fed back, and multiplies it. Now also notice our values are very arbitrarily chosen to be equal to 1, 1, and 1. All right. Now, in the previous video I made, I brought attention to this thing that I really like about PID controllers, which is that they respond pretty reasonably to impossible requests. And that quite often the impossible request is that you're asking for a step change in something like position, which is this is a position controller, right? I do want to talk a little bit about the plant, and for right now, just say it's a mass that's constrained to move in one direction, and it receives a force as commanded by the controller. Now, let's again though get back on this tangent that I think is pretty important, which is responding to an impossible request. Well, taking a derivative of a step that's going to be presented to the derivative block because of our unique command, well, that's an impossible request too. And so with controls, you're always coming up with real cute tricks. And so I'm going to just kind of bring your attention to this thing here, which we call a transfer function. And I'm going to just kind of demonstrate the idea by taking that, not that, let's hit the space bar, and let's get the scope as well. All right. And so how do you take the derivative of a step function? Well, the short answer is you don't. All right. And the way that you choose not to is that you smooth out that step function a little bit. All right. So let's paste all these blocks in here, and let me just kind of show the basic idea of this. All right. So let's set these up. Let's connect them. And in our scope, let's compare what we've commanded with what we get. And so we're commanding the yellow line, and we're getting the blue line. Okay, and it looks like a step function. Right? Zoom in, and I'll see that that little transfer function just rounds it out real nicely so that we get a valid assessment of derivative throughout, right? Now, the other thing I want to point out is that the parameter, and you can see it right there on the block, the key one is this first element that's defining, I'll call the denominator of the transfer function. And so I'm going to show that it essentially is a time constant. So by making it 0.1 or making it 10 times bigger than what we had before, you'll see that it, okay, I didn't do that very well. All right, so let's run it for 2 seconds. Okay, and please excuse that error in my performance. All right, but anyways, here it is with a value of 0.01. And now let's make that parameter 10 times bigger. And I just want to show the effect is to really draw out that transition to a much larger amount of time. Okay, and this is an important thing because it is a contributor to dynamics, which might be important to kind of tune as well to get the system uh, um, responding as optimally as possible. All right, so let's now get into this model and let's see how we might do better than what we got right here. All right, so again, it's taking us 1,000 seconds to settle with quite a bit of oscillation. All right, and I do want to show my plant. It's called F is equal to MA, right? But we get X out of it, right? And so if we look in here, we'll see that F is divided by M, and then we integrate it twice to take our acceleration to get velocity and then position. Okay. Now, when I do PID tuning, I kind of like to start with P, and so I'm going to go ahead and zero out both my integral branch and my derivative branch by making the gains equal to 0, right? And in so doing this, I want to kind of bring our attention back to this kind of idea that I've been talking about. That the PIDs are like rubber bands, okay? And I do kind of mean that in a complementary way, even though it doesn't necessarily sound like that. Um, but but I want to kind of address, more kind of functionally what I mean by that too. All right. In the most controls classes, as you're introduced to PIDs, they'll talk a lot about it's like a spring damper. And if you look at the P equation, which is I want X to be equal to a value, but it's currently equal to something different than that value. And so I take their difference and then I multiply it by a constant. Well, that's pretty much the equation for a spring. And therefore, if all you have is proportional gain, it's going to oscillate like a perfect spring, all right? Especially for a system like this, where it's simply a mass that's kind of moving on a straight line trajectory, all right? So with Kp being really like a spring constant, well, it turns out that the damping is really delivered by the derivative piece. And again, the equation matches perfectly, the classic damping equation, right? And so I'm going to put in a damping value of 1. So Kp is 1, Kd is 1. And let's hit run one more time. Now we'll see a very nice damped response, right? And we're still running it for 1,000 seconds, but we'll see that the transition is taking place much more rapidly now, probably like 15 to 20 seconds. All right. And our goal is to really kind of get it probably under 5. So let's alter our simulation time to 10 seconds. And now we'll kind of go to work to getting the response that we want. Now the step occurs at 1, and that's where everything starts changing. And you'll see within 10 seconds, it still hasn't exactly settled. All right. And so what I would do to address that is let's make Kp a lot bigger. I'm going to put in a value of 100. All right. And so it's just going to see what we get. All right. And so things are taking place very quickly. It kind of hits its first value of 1 probably in less than maybe like 0.2 of a second, but it's certainly a classically underdamped system still too. All right, and so it means we need to make KD a little bit bigger. All right, and maybe I'll make that 100 as well. Okay, and we might be happy with this. I'd say that's quite a bit of overshoot, and that the response though is very good at 0.1 seconds. Now, is that good for our mission? Well, I'd say 2 things I want to consider. All right, one is the overshoot is overshoot in the request of a step change, and that's not necessarily what we're going to do. And then the other thing I want to really kind of consider is how much force is it really asking for? All right, and so let's run the simulation one more time. This time we're scoping the force command. Right, and we're going to see it's asking for, what is that, 10,000 newtons? Well, for the actuators that I might have in mind, that's probably not going to happen, right? And so we'll kind of get into that in a second too. Right, and so one way to address, well, both the overshoot and the excessive force that's being exerted, requested of the controller, is to quit asking for a step. All right, and so I'm going to use my smooth transition block, and I think I'll take this and kind of compare it with what we get. And let's see. So we're going to, at that same time, we're going to request a transition at t equals 1 second. But this time we're going to ask for a transition time of an additional second. So so anyways, let's look at the difference here. All right, and I'll hit run. Right here, 2 seconds. And that all looks really good now at that point. Okay. And we're no longer requesting 10,000 newtons. We're down to a very reasonable 6. And we might decide, yeah, we're really good with this. That's a good control. Okay. And I'd say before we go to production with this, let's see. Well, I think there's a couple things I want to talk about. One is I want to talk a little bit about controls in general. Okay, so what we just kind of went through had nothing to do with physics. That whatever, that F equals ma thing is, that was already there. All right, that is certainly just a dynamic system that was going to produce a response that we operate upon with this really interesting math associated with a PID algorithm. Okay, and so my point on this one is that, and I'm kind of thinking about our conversation that we've had throughout this series on feed-forward control, which feed-forward control is really about knowing your system and using that knowledge of the system to anticipate what its response might be. And because of that, really, really good control ends up being very customized to what that system is. All right. And it turns out that that's true for feedback as well, but it's sort of like customized in a very empirical fashion, that you just keep on making adjustments based on response. The process of developing a feedback control system really is a feedback process itself too. Okay, and it's like things are treated as black boxes and we're turning knobs and we're getting things to work. And so just to remind us of that, I'm going to change the one thing that does essentially define our system here, which is its mass, and I'm going to make it 100. And I'm going to hit run one more time. And so if our mass happens to be 100 kilograms, this is not a good controller at all. Okay, so anyways, what I want to move into, and I think this will be in our next video, is this idea of feed forward. And it turns out that I'll say the formulation of what a PID is, it actually accommodates a feed forward controller quite well. All right, and at least if your dynamic system is a constant mass that's being accelerated by a force, right? And so I want to present that idea, and with this one, I want to maintain the idea of the usefulness of it being a rubber band as well. All right. And for feed forward systems, I think I've made this point or emphasized this point in the previous videos too, is that feed forward works if your understanding of what the system is, which is not only how big is the mass, but what its current state is, how fast it's moving, and what its current position is, and all that kind of stuff is, if that's well known. All right, and this rubber band makes sure that your estimate of what the system is, including its state of motion, is connected properly to what the real system is. And that's essentially a definition of what feedback is. So anyways, thank you. Looking forward to doing the next one.